This is the second part of the lecture on fracture mechanics. Until now we have been looking at linear elastic fracture mechanics and where it can be applied. Now we will go on to see how fracture occurs in different materials that may or may not follow linear elastic fracture mechanics strictly, and then we look at the end on what we call probabilistic fracture, where the variability of the defects comes into play. Here you see the picture of a cracked clay bed where you see cracking occurring extensively when clay dries up. So, different materials crack in different ways, and for that we have to understand what happens at a crack tip. In the case of the fracture in glass and ceramics, brittle fracture, as the stress intensity goes up near the crack tip, the stress reaches in the vicinity of the crack tip a value of stress which causes the rupture of the bonds in front of the crack tip. So, that is what we see here. We have the atomic bonds, and if we go back to the Condon-Morse diagram, we know that there is a maximum attractive energy that is keeping the bonds together, and when we stretch the bonds, what the crack is doing now is, as it is opening, it is stretching these bonds, and there will be a time when the bond energy is surpassed and the atoms or particles peel apart, break, the bond breaks and the crack now starts to extend. This is called cleavage fracture, which occurs due to the rupture of the interatomic bonds themselves. In metals, especially in metals that can undergo large plastic deformation, ductile metals, we have a different type of mechanism. We have what is called elasto-plastic fracture, that is, there is a plastic zone in front of the crack tip always, and this occurs for the following reasons. Now we know that in front of the crack tip we have high stresses. As we approach the crack tip, now the stresses will increase, and there will be a point in time where the stresses, according to linear elastic fracture mechanics, would be higher than the yield strength. So what happens is, the region where this stress can become higher than the yield strength now becomes plastic. So the stress over this region is always equal to the yield strength. So this becomes the plastic zone, and there can be cavitation forming and plasticity occurring in this region of width Ry. With further increase in stress, what will happen is this crack now propagates. In the microstructure, what happens is that these cavities that form now link up with the crack, or the crack extends to include the cavities. This would result in the blunting of the crack, because you will not have a sharp crack anymore. Here initially we had a sharp crack. Now with the inclusion of the cavities, the crack blunts, that is, it loses its sharp end. Since there is this blunting, now the stress intensity at the crack tip decreases, the stresses drop slightly at the crack tip. So this now requires further energy to propagate the crack, and there is an extension of the plastic zone beyond the crack blunting. So what we see is, first there is a zone which becomes plastic. With further increase in stress, this plastic zone joins up, or the cavities that form in the plastic zone join up with the crack. You have a crack extension, but a blunt crack forming. This crack blunting now requires additional energy to propagate the crack, because the blunting decreases the stress concentration, and then progressively there will be a plastic zone formed ahead of the crack, and the crack will extend. So there is a toughening effect or a beneficial effect to arrest the crack due to the formation of the plastic zone, ductile tearing and crack blunting. In metals it is common even in practice to stop a crack from propagating by drilling a small hole at the edge of the crack, so that the crack sharpness is lost and you have a blunt crack. This plastic zone that forms in front of a ductile material that is cracking can be quantified. As we said, when the stress close to the crack tip reaches the yield stress, there will be a region where it is yielding over a distance r y. Plastic deformation occurs in this region, and we can consider that the stress over that region is equal to the yield strength. The value of r y, which is the width of the plastic zone, is given by this k1 square divided by 2 pi sigma square y when there is a state of plane stress. So, what we see here is that when sigma y is larger, r y is smaller. That is, for a material which has a higher yield strength, the plastic zone is smaller. That means the ductility of the failure is also less. Larger the r y, more ductile is the failure, more energy is dissipated, there is a larger zone where the toughening of occurs and energy is dissipated during failure. And this also explains why materials, even ductile materials that are stronger, behave in a more brittle manner, and the origin is the size of the plastic zone that develops in front of the crack, which is smaller when the yield strength is higher. Metals that contain inclusions also end up having elongated cavities, like we saw in the picture 2 slides back, and these cavities now link up and cause ductile tearing, and this blunts the crack, as I explained, and this blunting of the crack lowers the stress concentration. After the lowering of the stress concentration, now the stress decreases, and to further propagate the crack a higher stress is needed. However, the blunting of the crack also leads to work hardening. This again strengthens the material in front of the crack and again leads to higher stress requirement for propagating the crack. So, all these mechanisms that occur in front of the crack tip in a ductile material tend to increase the energy requirement and therefore arrest the crack and slow down the propagation of the crack. We see a difference in the plastic zone size depending on whether the conditions are close to plane stress or plane strain. In plane strain, there is a confinement of the region, there is a restraint, and therefore the zone is small compared to when you have plane strain, when you have plane stress. The plastic zone in plane strain is smaller than the zone that we have in plane stress. Suppose we have a very thick element, we will have plane strain in the middle because of the confinement, and on the surfaces we have plane stress. And if you look at the development of the yield zone in front of the crack in a thick plate, metal plate, we will find that there will be a larger yield zone in front of the crack tip at the surfaces due to plane stress conditions, and inside it will be smaller. This is shown in this picture of fracture occurring in an iron specimen. On the left we have the front surface, this is now the crack or the notch that was made, and this is the plastic zone that is occurring in front of the crack. On the other surface, the back surface, again now we see this is the notch, this is the crack tip, and this is the plastic zone. Now, if we were to take a section across, we will see that on the edges we have a large plastic zone corresponding to the regions of plane stress, but in the interior, due to the confinement, due to the constraint, we have a smaller region of yielding because of plane strain conditions. How do other materials like polymers fracture? Just like we see a competition of fracture and yielding in metals, polymers also have a competition between cracking and shear yielding or crazing. Shear yielding is similar to what we see in the yielding of metals due to plastic flow, but here in a polymer the molecules slide with respect to each other, the molecule chains in the polymer slide with respect to each other, and we can have yielding occurring or something similar to yielding occurring. Crazing is more localized, that can lead to cavitation and very high strains occurring, and if you see crazing occurring in a polymer, you would see that there is a whitened zone, a zone becomes more opaque in front of the crack tip called the stress whitened zone, and this forms perpendicular to the maximum principal stress. So what happens in crazing is that we have very high strains, so the polymer chains now get aligned in the direction of the applied stress. So this is the direction where the crack is propagating, perpendicular to it these molecules start aligning. This now bridges the crack, but also leads to cavities forming or voids forming between these aligned molecules. These aligned molecules are called fibrils. Little bit away from the crack, this is what you will see, or a little bit when you zoom out of the crack, you will see that at the crack tip you see these fibrils bridging the crack, and then you have the voids occurring. So these are the fibrils at the craze zone near the crack tip. Some more pictures, we see the on the top we see the stress whitened zone or the crazing zone near the crack tip, and closer we see the craze zone in polypropylene. So you see the fibrils here, the voids, and this is now the craze zone. In the microscope, when we look across the craze zone, we will see this in polypropylene. This is now the section of the fibril, all the bunches, the bundles of fibers, bundles of the polymer chains, and here between or outside of the fibrils we see the voids or the cavities occurring. So this would be the cavity and bounded by the fibril. What happens in composites? Suppose we have fracture occurring in wood or other materials reinforced with fibers or inclusions. The fibers will tend to arrest the crack, they will stop the crack from propagation. That is, first you will have the crack occurring in the matrix, say in the polymer matrix the crack is propagating, with higher stress the crack propagates further and it reaches the fiber. Now the fiber is stronger, has a higher elongation capacity, so it will stop the crack from propagating, it will not allow the crack to break the fiber and propagate. So what we see when the stress continues to increase is now the crack envelops the fiber and it does not propagate, does not extend further until the fiber is either broken or it slips and you have significant deformation in this region. So this gives rise to two phenomena that help control the crack. One is the crack is now blunted, instead of a sharp crack we have now a blunt crack tip. So this decreases the stress concentration and therefore you need now more stress to keep the crack propagating. Secondly, some of the stress now is transferred by the fiber. So there is less of a driving force for continuing the crack, because some part of the stress now is transferred from one side of the material to the other by the fiber itself. So the toughness of the polymer is increased significantly when fibers reinforce polymers, they act as crack arresters, they deflect the crack and they blunt the crack tip. When we have inclusions, similar effect occurs. The load need to propagate the crack becomes higher as the inclusions, as we saw in the case of fibers, increase the fracture energy, the energy requirement to keep driving the crack. What would happen when we have rubber inclusions in a polymer is that when the crack propagates, we have these rubber inclusions acting like springs. They bond the faces of the crack, they pull the faces of the crack together, and until the rubber inclusion breaks, the crack cannot propagate very much further. So, this tends to close the crack, and as the crack propagates, it will encounter more inclusions which will again arrest the crack, more energy will be required to break these rubber particles and keep going. So, rubber toughened polymers derive their toughness from the bridging of these small rubber particles. They act as springs and tend to close the crack. What happens in concrete? Concrete, as we know, is a heterogeneous material, it is a very brittle material, and in front of a crack tip in concrete we have what is called a fracture process zone, and in this zone there are many mechanisms which occur which prevent a very brittle fracture from occurring. Near the crack tip we have fibers, in case this is a fiber reinforced concrete we would have fibers, otherwise we have also aggregates which are interlocking or aggregates that are bridging a crack. The aggregate has either to be broken or pulled out for the crack to propagate. The aggregate also deflects the crack. If there is a very hard aggregate here, the crack will rather go around if the interface is weaker rather than going through the crack. There is also some micro cracking due to the defects that occur. So, all this together dissipates energy during cracking, and this is called the fracture process zone, which occurs in front of the traction free crack, that is the crack, the part of the crack where there is no bridging between the crack faces, that is called a traction free crack. The size of the process zone determines the toughness of concrete. Larger the process zone, higher will be the toughness, similar to what we saw in yielding of metals. The process zone will be larger when we have a material such as fiber reinforced concrete, and the process zone will be much smaller when we have a brittle concrete like a high strength concrete where the toughness is lower. Since toughening mechanisms in materials like concrete, rock and some ceramics are weak, they are called quasi brittle materials. They are not brittle as glass, but still close enough, and they are called quasi brittle materials, that is almost brittle materials. How do we model these mechanisms? We understand that since there is a zone where energy is dissipated that occurs in front of the crack, we cannot apply linear elastic fracture mechanics directly. So, there are different models, the simplest of which is called the R curve model as part of nonlinear fracture mechanics. Here what we do is, instead of a constant fracture energy, the GC that we saw earlier in the fracture criteria according to linear elastic fracture mechanics, we have a variable fracture energy called the R curve. The effect of the toughening that we saw in many of these cases in this lecture is represented by an increasing or a rising resistance curve or R curve, where the critical energy release rate, earlier we called it GC when it was constant, is now changing with crack extension, that is it is increasing with crack extension. So, this curve will tell us how we apply this R curve. It looks complicated, but let us see how to understand how it works. On the x axis we have crack extension, say initially we have a crack length or a defect length of A0. As the crack propagates, we will move from left to right. On the y axis we have both R, which is the resistance or the variable fracture energy. Instead of a constant fracture energy, we are now having a fracture energy that is increasing with the crack size. G is the energy release rate that we discussed in the previous lecture. The material property is this curve, is the R curve. So, this is now a material property. Instead of a constant, we have a curve, fracture energy as a function of the crack size. So, what we are saying is as the crack is extending, more and more of these toughening mechanisms come into play, the process zone becomes more prominent, and therefore, the resistance to crack propagation increases. These lines are the energy release rate as a function of the applied stress. As we know, the energy release rate now will depend on the load or stress applied, the geometry of the element, and the crack length, just like in the case of K1. In this case, the G curve cuts the R curve at this point. So, that means this is the stable crack length for this stress. Now, we increase the stress, we have a stress sigma 2, and the corresponding curve for G is this. So, the crack length is slightly longer, the crack propagates a little bit, but still it is stable, it does not run away and have catastrophic sudden cracking. Sigma 3, the crack extends little bit more, because it now encounters more resistance and it stops after propagating little bit more. But beyond this, at sigma 4, we find that we reach a point where any further increase in stress will create more G than R. So, at the point where we have the G and the R curve meeting and the G curve is tangential to the R curve, instability starts. Any further increase in stress will cause a sudden increase in crack length and we will have failure. Until this point, the crack can propagate in a stable manner, keep increasing, encountering more resistance and stopping. The growth does not increase suddenly. So, as this applied stress increases, the energy release rate G increases, and when the G function becomes tangential is when the crack extension stops being stable. Until that point, the crack extension is stable, that is, it is slowly progressing, but it stops when the stress does not increase any further. So, the criteria for stable and unstable crack growth for the R curve are defined as follows. For stable crack growth, we have two conditions, G equal to R, and the slope of G with respect to the crack length should be less than that of R. So, as long as these conditions are satisfied, we have stable crack growth, that is, the crack grows, but it stops at that stress. If the crack growth continues due to higher stress, this means that the slope has now increased for the G curve higher than that of the R curve. This is when failure is said to occur, there is unstable crack growth occurring. A more complicated and more comprehensive set of models are called the cohesive crack models, and this started when two people, Dugdale and Barenblatt, independently proposed models for looking at plastic fracture, where they considered the crack which was traction free and with a plastic zone at the ends, and this plastic zone comes about because of the mechanism that we discussed in the beginning of this lecture. There is yielding, there is cavitation and so on occurring here. So, the stress here is equal to the yield strength, that is what we saw. So, what Dugdale and Barenblatt did is that they said that to represent this, we can take a traction free crack, say a linear elastic crack, and add these closing stresses at the end equal to the yield strength. So, they superposed two solutions, one a crack without any stresses like a linear elastic crack, and then they superimpose the stresses at the end to give the solution for this crack with a plastic zone. So, in these models the plastic zone over the length rho ahead of the traction free crack 2a of length 2a is modeled as a crack of length 2a plus 2 rho. Okay. So, this is the whole crack with the closure stresses equal to the yield strength over this ends of the crack. So, what they did is represent the elasto-plastic fracture by superimposing two elastic solutions, a through crack, a traction free crack under the applied remote stress, and then the behavior of the crack with the closure stresses. The first part is a through crack under the applied stress, remote stress far away from the crack tip, and the other solution which is superimposed is the crack with the closure stresses at the tip. A further extension of this model called the fictitious crack model was given by Hillerborg in 1976 with applications to concrete and other brittle materials. Here instead of a plastic zone, we saw that a fracture process zone forms. This is what we saw in the case of concrete. So, obviously there we do not have a yield strength that is governing the stresses across the crack tip. So, and a more flexible model has been suggested where we have a crack with the ends having these cohesive or closing stresses that could be defined depending as a function of the material. And a possible function for these closing stresses is given here, where we have on the x axis the crack width, that is the opening of the crack W, and on the y axis we have the stress that is trying to close the crack. This is the closing stress or the cohesive stress. At the crack tip where the crack is just starting to open, the stress will be equal to the tensile strength, because when the strength is exceeded, that is where cracking will start. And far away from the crack tip, we reach a point where there is no closing stress at all, that is the crack is significantly separated, that all the mechanisms that cause toughening are nullified. This is called the critical crack width, W sub c. The area under this curve is called the fracture energy. Okay. Gf is the fracture energy. So, the fracture criteria according to the cohesive crack are a combination of these three. At W equal to 0, that is at the crack tip being 0, crack is just about to start, the stress across the crack is equal to the tensile strength. Far away from the crack tip at a distance where we have a crack width equal to the critical crack opening, W equal to Wc, there is no more closing stress or cohesive stress. And then we see that the integral of the closing stresses as a function of the crack width integrated between 0 to Wc is called the fracture energy. Okay. So, we have this as a parameter, the tensile strength as a parameter, and the critical crack opening now as a parameter, in addition to the shape of the curve. The shape of the curve also can vary from one material to the other. Now, this representation can be used in finite element analysis and any other analytical technique to represent the tensile cracking response of materials such as concrete, rock, ceramics, even polymers. When we have other modes of fracture, this curve can be modified to include the effects of mode 2 and mode 3, but it has been very much used in the more critical failure that occurs in these materials, that is in mode 1. So, let us see some simulations. This is from sim science, where we see the simulation made by Frank 2D, which is a finite element code coming from the group of Professor Tony Ingrafia in Cornell University, where they have used fracture mechanics to simulate what happens in a dam that is subjected to excessive height of water. The pressure of the water creates a crack in the dam and you see a crack propagating. The red zone is where we have a very high stress concentration, and we see how the model is able to show how the crack will propagate and ultimately how the dam will collapse. Another simulation is from the group of Professor Bolander from the University of California, Davis, where we see a simulation of concrete overlays subjected to shrinkage. On the left we have an overlay that is plain concrete, on the right we have an overlay that is fiber reinforced concrete, and this is what is expected to happen due to shrinkage over a period of 100 plus days, and this was simulated using their software called FEMLab. You see on the left that the shrinkage causes stresses in the overlay which cannot be resisted by the plain concrete. The fracture toughness is not that high, so we have a crack through the overlay at several places. In fiber reinforced concrete now, the fibers cause toughening, there is a higher fracture toughness of the overlay. So even though there is shrinkage, the overlay does not crack, but the deformation causes a delamination running through the subbase instead of creating cracks in the concrete. A third simulation that I am going to show you is from the Madison group, where we have the case of a PVC pipe, and this has been simulated to show how the pipe will crack and fail when there is excessive internal pressure. So you see here the crack opening, this is the section, and here you see the longitudinal view how the crack propagates. So such type of fracture analysis can be used to determine how materials will fail, how structural elements will fail, and this we can use for design to prevent such failure from occurring, and also to have better materials developed that can resist such type of failures. Now we will go on to probabilistic fracture of brittle materials, and for the transition I have included this photograph of a traditional house in the Kulu Manali valley, which has a lot of repetitive elements. It looks like a simple house and it is made out of wood and stone, and we have a lot of repetitive elements, similar looking elements like these pillars on the balcony, and these walls are all made of blocks of stone. Though all these materials look similar, each of them will have a different set of defects. So when we look at the failure of a brittle material, these defects and the variation of these defects from one element to the other, even though the material is all the same, can affect how fracture occurs. So materials like glass, ceramics, rigid polymers, concrete, to some extent wood, have low fracture toughness. This we saw in the previous lecture, and this makes them vulnerable to the presence of defects that can cause cracks or crack like defects. These materials are therefore called defect sensitive materials, and they are prone to brittle failure before they can have yielding type of failure. So they crack and fail rather than yield and fail. Also what we see is most of these materials also have cracks and flaws in them, they are not without defects. This combined with the defect sensitivity decreases their tensile strength significantly. Concrete can have inherently flaws in the order of 5 to 10 millimeters. Normally you would expect flaws to be at up to the size of the aggregate. Bricks and stones have smaller defects in the order of a few millimeters. When we have engineered ceramics that are made in the factory under very well defined conditions, controlled conditions, we can have smaller defects, say in the order of a few microns. So, let us look at how a piece of material subjected to tension and compression differ in their behavior. On the top we have a panel subjected to uniaxial tension, and in this panel now we will have a lot of defects. This is the inherent defects occurring in the material, and now when tension is applied we will have the most significant crack, that is the longest most favorably oriented crack. We know that under tension cracking will occur perpendicular to the direction of the applied stress. So, this being the largest most favorably oriented crack will start to propagate. Tension occurs at the ends of the crack and you will have propagation and ultimately failure. So, what we see is under tension a single crack dominates failure. It is the largest crack or largest flaw that will become a crack and fail. Now, let us see what happens if the same specimen, instead of subjecting it to tension, had been subjected to compression, uniaxial compression. Okay. What we find is this crack which dominated the failure in tension does not do anything, it is just going to close, whereas the more inclined cracks will have tension and compression at the ends. If the inclination is such and you have a vertical loading, you will have tension and compression occurring, which will tend to cause some sort of splitting stresses at the ends. You see here that at the end of the crack we have crack extension occurring almost vertically due to splitting, and just one crack does not cause completely failure. Now, many of these cracks have to open up, some of these cracks have to join before finally you have failure under uniaxial compression. So, we see a big difference in how failure occurs and how the flaws will lead to failure in tension and compression. Under tension failure occurs by the propagation of the longest most favorably oriented flaw, that is one flaw can control the failure, and it is obvious to understand that in different specimens you will not have the same flaw size and the same orientation of the flaw, and therefore there will be a large variation when you test many specimens. That is why we find that the variability of the tensile strength is much higher than in compression. Also, now when we look at compression, we noted that cracks will propagate in a stable manner, change orientation, you saw the inclined crack becoming vertical at the ends. Many cracks have to join, propagate and join to cause failure, and consequently the failure is not dependent on the characteristics of any single crack, but an average. Many cracks contribute, many cracks have to propagate stably, join together and crack. So, this has two important consequences when we compare compression and tensile behavior. The compressive strength of brittle materials like concrete, rock, ceramics and so on is about 10 to 15 times that of the tensile strength. Because you have many cracks propagating, the cracks have to change orientation and join together and cause failure. The other thing is the variability of the strength is much lower in compression than in tension, because here you are averaging the behavior. Even though the crack distribution between specimen and specimen change a lot, since many cracks have to contribute, we get an averaging of the behavior and therefore the variability decreases. So, to do it correctly we have to look at the statistics of strength. These flaws can vary in size and orientation within the specimen itself, and from one specimen to the other there is a statistical variation in the strength given like this. This could be tests conducted over several identical specimens and you will see that there is a variation of the strength. Not all specimens will fail at a certain value. Depending on the flaws, if there is a large flaw by chance, you will have a less strength. If you have a specimen with very few flaws, then the strength will be higher. So, instead of defining a single tensile strength, it is probably more appropriate to look at a probability that the specimen or body has a certain tensile strength. That is, we say that there is a probability that the strength is at least this much, or there is a probability that the strength is at least this much. And this can be looked at when we see the experiments on different materials. This is how we have test data. This is the test data from boron filaments under tension, and we find that there is a variation of the strength that we get. This is the number of tests, and we find that lot of tests fail in this region, but there are also a lot of specimens which fail with lower tensile strengths. Some fail at a higher tensile strength. So, there is a certain probability that the strength is at least 3 gigapascal, and this probability is quite high. If we take 4 gigapascal, the probability is quite low that the strength will be at least 4 gigapascal or more, because we see that lot of specimens fail at lesser values. Similarly, with other materials like carbon fibers, we have a similar distribution, and we see a variation of the strength from specimen to specimen. We also see that the volume of the specimen will dictate how failure occurs, because the distribution of flaws, the occurrence of large flaws will vary depending on the size of the specimen. So, the distribution of flaws and crack lengths are related to the volume of the material being considered. A large specimen or large sample of the material is more likely to have a larger flaw than a smaller one. This is very important. A larger specimen has a higher probability of having a large flaw, preferably oriented, than a small specimen. Therefore, generally we find that the average tensile strength of a larger or longer specimen is lower than that of a smaller or shorter specimen when we have brittle failure. These two are related. We said that a larger specimen or a longer specimen can have a higher probability of a large flaw. So, on the average what happens is, when we test a lot of these large or long specimens, we get an average tensile strength that is lower than if we test lot of small or short specimens. And this is further illustrated by this diagram from Ashby and Jones, where you see a panel with many flaws, and in this case the most critical flaw is this. When this flaw, which is the largest flaw, propagates, you will have failure. Now, instead of this large specimen, suppose we had made small specimens from the same piece of material. The probability that we got exactly this piece, this small piece, is very low. We could have made specimens from here, from here, from here, and so on. Suppose we had made a small specimen such as this, denoted as B. Instead of this specimen denoted as A, we would have a small flaw instead of large flaw. This will give a higher tensile strength than this one. So, what we see is, in a large specimen there is always a higher probability of a larger flaw than in a small specimen. And this is something that goes back to the tests of Leonardo da Vinci on wires. He did tensile tests of wires with this experimental setup that is shown here, where the wire was tied to a bar and on the other end to a wire basket, and sand was added to this basket until the wire broke. Then the quantity of material in the wire would be measured or weighed, and the failure stress was calculated. So, what he found was, when he had different lengths of wires all having the same cross section, okay, the cross section is the same. So, theoretically the stress is the same if the load was the same, because load by area is the stress. What he found was, different lengths of wires failed in different ways. What Leonardo da Vinci found was that the longer wires were weaker than the shorter wires. Remember, all are of the same cross section. So, this conflicted with classical materials mechanics theories, where strength does not come into play. Remember, in the previous two lectures when we looked at the material response, we always talked about a strength, we talked about a stress, but we never brought in the size or the shape of the element to determine what the strength would be. So, this was considered to be a mistake in Da Vinci's notes and ignored for a very long time. But now we know that Da Vinci's observation is in agreement with what is called the weakest link theory. The weakest link theory says a chain is only as strong as its weakest link, and the longer the chain, there is a higher probability of a very weak link. Okay. So, the same argument for a wire would say that a wire would have the strength of its weakest section. A longer wire has a higher probability or likelihood of having a weaker section than a stronger one. A weaker section means that with a longer flaw. This was shown in extensive tests by Griffith in the 1920s, and these results are from tests of glass fibers. Instead of different lengths, what he did is different diameters, and what he found was, as the glass diameter decreased, when we went to very thin glass fibers, the flaws were eliminated and therefore the strength went up. Strength even went up to 11 gigapascal in a glass with a bulk strength of 170 megapascal. A large specimen would fail at a strength of 170 megapascal, but very thin fibers could take even 11 gigapascal of stress, and this strength decreased as the diameter increased. As we increase diameter, there is a higher probability of defects and flaws. This also explains to us the effect of the critically stressed volume. When we have a specimen failing in a certain way, and so many times we have tension occurring not in this manner. Here we have the panel that we have discussed until now, where we have a specimen subjected to uniaxial tension, and here any flaw anywhere can control failure. However, if we have a splitting tension test, only the flaws in this region, because this is where the high stress is, will control failure. Further, if we have a beam, only the flaws here will control failure, because this is where the high stress is. Here we have a uniform stress state. So, any flaw anywhere here can lead to failure. Here a flaw here will not control the failure, only those flaws which are in this region. Again, a flaw here in a beam will not cause failure in this configuration, only here. And here this critically stressed volume is very small compared to this, and this is an intermediate case. So, what we find is this case will give the highest strength, because the critically stressed volume is the least, followed by this, followed by this. And in the case of concrete, this is evident from tests that the splitting tensile strength is about 10 to 15% higher than the uniaxial strength, and the strength from a beam can be 50 to 100% higher than what we get in uniaxial tension. And this is all due to the effect of the size of the critically stressed volume as a function of the loading configuration on the strength. So, how do we model this? We saw that in all the three cases failure occurs due to tensile cracking, and the maximum stress occurs just after crack initiation. The crack does not propagate lot, but it fails suddenly. The volume of the material taking the peak stress is different in each case, that is, the volume of the material where the crack can initiate differs. Only the flaw size within this material matters. So, we have to find out what is this volume and use this volume as a measure of the variability of the flaws. Strength is higher when this volume is smaller, and it is independent of the total volume of the material, especially when the stresses are non-uniform. One of the ways of tackling this problem is through what is called the Weibull model, Here we look at survival probability of a specimen of a certain volume V0 subjected to a tensile stress sigma, and this is the survival probability. The probability that a sample subjected to sigma stress of size V0 that it will not fail is given by this. Sigma 0 is the mean strength of the material, m is what is called the Weibull modulus. Lower the Weibull modulus, higher is the variability, and lower is the probability of survival at that particular stress. This distribution is shown here. Ps is the survival probability. On the x axis we have a ratio between the applied stress and the mean strength of the material, and what we find is that when m is very large there is a very definite drop. There is a very good probability that the failure strength is going to be sigma 0. However, when m is smaller there is also a probability that the strength is smaller or larger. The variability is there. M for brick and concrete is about 5, for ceramics it is about 10, and for steel it is about 100. And when we have a material with a Weibull modulus of 100, we can say that it has a well defined tensile strength like we see here. These are tests showing data from steel, alumina and a processed alumina. We find that the slope is higher for a conventional alumina ceramic. For steel it is almost vertical, that means m is very high, there is a very high probability that failure will occur only here. For a conventional alumina there is a probability that there could be failure anywhere here. Alumina the modulus is higher, for CPS alumina, a processed alumina, the modulus is higher, for conventional alumina the modulus is around 5. So from tests like this we can calibrate the Weibull model to get the value of m. Further we have to bring in the effect of the critically stressed volume, and we modify now this equation to say that if V0 is the volume of the tested sample that we tested say in uniaxial tension, and the parameters of the Weibull model for this material are sigma 0 being the mean strength and m being the Weibull model, the survival probability of a sample of any other volume other than V0 or a volume with a critically stressed volume other than V0 say V is given by this log natural of the survival probability of this volume V is minus V by V0 times sigma by sigma 0 elevated to the power m. So this is now the final design equation that gives both the effects of applied stress and critically stressed volume on the survival probability, and this can now be used to compare different materials and find out what would be an acceptable stress value for a specimen with having a certain volume or a critically stressed volume and knowing the stress that is applied on it. So to conclude, we have looked in this lecture at different fracture mechanisms, how we deal with fracture, how we model fracture, and at the end we also looked at probabilistic fracture where we saw how the defects and flaws can come into play. There are a lot of references that you will see on the screen that you can look at. There are many good books on fracture mechanics and lot of information on the web also. Thank you.